Okay, so this is the SN1 video. Did SN2. SN1 and SN2 reactions are what will have to be decided upon, at least on this exam, for and for the Atlantic University Orgo 1 exam number 2. So let's go through the anatomy of a reaction, right? We did SN2 before and talked about all the different things that we have to be aware of with SN2. And what's important to note is that these trends, like these nucleophilic trends, still apply. Leaving group trends still apply to SN1. They don't change depending on like the trends, the periodic trends don't change depending on the reaction. They stay the same. Now, what does change is what the reaction prefers, right? But earlier we talked about these leaving group trends and periodic and nucleophilic trends, which are really important, and they still apply. But let's go to SN1. So here we have a reaction. We have this bromine species reacting with water to make some kind of product. So the first thing you want to do with any of these reactions is for me, I like to try to I want to figure out what's the purpose of each piece of this reaction. Okay. And so again, before with SN2, we talked about how important the leaving group was, right? And the leaving group is important for SN2 because we wanted a primary, secondary, tertiary in order of most important to least important, right? Because for SN2, that nucleophile was coming, hold on, I'm gonna be right here, I gotta zoom in just to be more specific. That nucleophile was coming in and attacking, right? And you didn't want a bunch of stuff sticking out of that carbon. Like you it's not going to happen with a tertiary alkyl halide just because of how much space there's not for this molecule to fit in. So for SN1, we have a reverse of the trend. Okay. SN1, we have tertiary is greater than secondary, which is greater than primary. But the question is why? Beforehand, this primary, secondary, tertiary motif was important because of the way SN2 liked reactions, like the environment it preferred. Same here. SN1 wants a tertiary alkyl halide, or leaving group, sorry, but a tertiary alkyl halide usually, because the first step is not nucleophilic attack. The first step is actually this. The leaving group leaves first. So why is that important? It's important because that's why you want that tertiary, secondary, primary. Because when the leaving group leaves, you make a carbocation. And carbocation stability goes tertiary carbocation, secondary carbocation, primary carbocation. So that's why we want a leaving group that's big, again, so that big leaving group still applies, right, because it needs to leave. But we want, what's more important for this one, instead of the nucleophile being super important, right, like SN2, where we needed a strong nucleophile to kick off that leaving group, the nucleophile is not that important here because nucleophilic attack is not the first step. The shift of importance goes to here, right? Among some other things, but mainly here because that's what's going to affect that carbocation stability, right? We want that stable carbocation. So the first step is the leaving group leaves. Then the second step is nucleophilic attack. And it's important to know that we don't need a strong nucleophile simply because the nucleophile is not attacking in the first step. So it doesn't need to be strong. It just needs to be there to be able to do something. Okay, so Now the questions aren't going to be all tertiary. What you'll find is that you'll have to decide between a lot of secondary alkyl halides, and what you'll need to look at is the the nucleophile, also the solvent, but mainly the nucleophile. So here, let's talk about stereochemistry. I'm not going to use yellow because it's just a little too bright. Stereochemistry is very important. SN2, remember, SN2 was an inversion, right? It would go to R to S or S to R, right? It would go from wedge to dash, dash to wedge, right? SN1 SN1 is an inversion and also a retention. Okay, so let's actually do this to make it a little bit easier. If we make this wedged, okay, there we go, because I was tripping. Hold on. Let me go here. Oh, okay, sorry. Playing big games. We need to start over here. Okay, what I'm doing is editing this because I need to show stereochemistry. Also, you can also get problems where stereochemistry is not shown. There we go. Okay, there it is. So here we have a wedged bromine. Okay, and that's cool. So now I can make my point. All right, so we're going to have, like I said, a retention, right? And the retention is in like, it's going to stay wedged, and this is wedged. And we're going to have an inversion, right? And we're going to have an inversion because the nucleophile is going to attack from not only the backside, like only what SN2 does, but also the front side. So the front is what maintains the stereochemistry. The back is what flips the stereochemistry. Also, one point to note, so you're going to have retention and inversion, right? So be aware of those two possibilities. Also, in the process, if you have a water or like an alcohol, one of those hydrogens is going to get pulled off. So it's going to end up, water's going to end up being an alcohol simply because water doesn't like to be bound to stuff. Okay, so that's the gist of SN1. Let me just go back through it. So we said that SN1 was different because instead of the nucleophile being an important piece of attack, we want a tertiary to a secondary alkyl halide because it's the alkyl halide or the leaving group that's going to leave first. So we need to make sure that when it leaves, it's going to leave a stable carbocation. Okay? Now, there are examples of reactions where the leaving group leaves and then you end up having like a ring expansion, but we're not gonna go into that just yet. I'll do a video on ring expansions, but that carbocation wants to be stable, right? Which is why the leaving group leaves first, okay? And the bigger leaving group is still what it wants. And these things also affect the speed of a reaction, okay? One thing I didn't say is this leaving group leaving first is the rate determining step, right? This step determines how fast the reaction goes. It takes a little while, okay? It's slow. It's a slow step to pop off that leaving group. So secondly, once the leaving group leaves, then our weak nucleophile will come in and attack from not just one side, but two sides, making a retention of stereochemistry, right? There's a wedged, and then we have a wedged here. And an inversion, right? It'll stay the same and it'll flip. Okay, both will happen, or both are possibilities. Okay, so what you'd see is this, and then the answer might see plus enantiomer, or you might see this one plus enantiomer. You won't see both options as the answer choices, but one of them will be right, and because of one's right, if one's right, then you know the other's the enantiomer. So that's the gist of SN1. I just wanted to go through the mechanism and how it works and what's important in it. And so SN1, SN2 reactions are not that bad. Let's just go back. I'm going to go back and do a little brief review. SN1 wants tertiary, secondary, then primary because it wants a more stable carbocation. SN2 wants primary, secondary, tertiary because it wants less stuff getting in the way in order for the nucleophile to attack. Because nucleophilic attack is the first step, right? Whereas for SN1, the first step is a leaving group leaves. Moving down, again, we need for SN1, we want a weak nucleophile. But for SN2, we want a strong nucleophile, right? Because the first step in SN2 is an attack. The second step in SN1 is the attack, right? So the steps of the attacks are different, okay? And then we have our solvent, polar protic, polar aprotic, and I'll make a video on like how the trends do sort of change in the solvent, okay? And so some of them change. So and then for SN1 you got an inversion and retention of stereochemistry. SN2 you have an inversion of stereochemistry only, okay? So only reason why I didn't bring up these is that I just didn't want to make this video too long. So, but I will bring them up because the solvent will actually affect the trends. But these trends you need to be aware of. So I apologize when I said the trends stay the same, as in like some will be the same, but for the most part, like depending on the solvent, you have to, especially these, for example, these ones will like flip a little bit. Anyway, that's SN1 and SN2.